Good. What kind of notation did I call this? Well, we called this sigma notation, right? And we said that we can evaluate these expressions, right, by taking the values, starting at the bottom of the sigma, plugging them in, and working our way to the top, right? So if I start at 1, I would have 1 squared, plus I'd have 2 squared, plus I'd have 3 squared, right? And that's just how our sigma notations work, our summations, right? Put it all together, and we get 14. Okay. Well, what am I showing you here off to the side for example B? Well, what I'm saying now, bless you, is when I plug these values in, I can be left with some algebraic expressions, can't I? So if I started at 0, what would I have? I would have x to the first over, what's anything to the 0? 1. Yeah, so I would have x. Okay, if I plugged in 1, I would have x squared over 2. If I plugged in 2, I would have x cubed over 4. If I plugged in 3, yep. If I plugged in 4, and if I plugged in 5. And so what's interesting about this, guys, is that I can create kind of functions, right? Using sigma notations and summations, right? That okay? All right. So I'm going to formalize what we did last class. Here I have a curve. I have a beginning. I have an ending. Everybody agrees that there is some area that exists under the curve bounded by the x-axis between those two values of a and b, right? Okay. So what I want to do is this. I'm going to do a number of different things here, but the first thing I want to do is I want to show you guys what the mathematicians years ago did. So years ago, the mathematicians said, okay, I want the area under this curve between a and b. If I asked you how long the domain is, well, how long is the domain? A to b. Okay, so give it to me as an algebraic expression. B minus a, right? So if this was 10 and this was 1, this distance would be 9, b minus a. Okay? So the width is b minus a. Now, I'm writing this as a fraction because what am I going to do to this width? Well, I'm going to create some rectangles underneath it, aren't I? Well, let's suppose that I wanted to create 4 rectangles. How wide is each of them? B minus a divided by 4. If I wanted to create 8 rectangles, how wide is each of them? B minus a divided by 8. Okay, so the width is going to be b minus a divided by n, where n equals the number of rectangles. So that is the width, right, of each individual rectangle that we're going to use as one of our dimensions to find the area, right? Okay. So if I want to do a left side approximation, what am I going to do? Well, I'm going to start on the left-hand side, and I'm going to go to the top of this rectangle. And I'm going to go to the next rectangle and go to the left-hand side. And I'm going to go to the next rectangle and go to the left-hand side. And I'm going to go to the next rectangle and go to the left-hand side. So for a left-hand side approximation, those would be the 4 values that I would use to represent the what? What does that create? Well, that creates the height of each of those what? Each of those individual rectangles, right? So this rectangle now has this height. And this rectangle is this height. And this rectangle is this height. And this rectangle is this height. Everybody cool with the left-hand side, how I created those? Okay, hold the thumb. So, how do I find the area of a rectangle? Well, I do the width times the length, right? And then I do the width times the length, and then I do the width times the length, and then I do the width times the length. I'm going to take those four things and add them together, right? So the left-hand side, I'm going to call it L4. The reason I'm going to call it, actually, I'm not going to call it L4. I'm going to call it LN. Because I don't know how many rectangles I'm going to have, okay? So I'm going to do this very generally. Do you guys agree that one of the dimensions for all of these is this? Right? So this is going to get multiplied by that. It's going to get multiplied by that. It's going to get multiplied by that. It's going to get multiplied by that. So I'm going to take b minus a over n, and I'm going to multiply it by each of those things. What am I going to call this first dimension? What is this called? What is this length? F of a. Isn't it just f of a? It's whatever y value I get when I plug in a, it's going to bring me up here. Okay, now I need this dimension. How do I get that dimension? Well, it's got to start at a, right? And what do I have to add to a? I have to add the width of a rectangle, don't I? Okay, I want to say this again. I'm going to start here. I need to get here and go up there, right? Well, to get here and go up here, I have to take whatever this value is and plug it into the function, right? So the question is, what is this value? Well, it's a plus a width. So isn't it really f of a plus this? Does that make sense? Okay. So what does that do, guys? It starts here and it brings me to this, and then I plug it in to go there. All right, so now to get to my next one, I'm going to start at A and I'm going to go over two widths, right? Make sense? And then to get to the next one, I'm going to start at A and I'm going to go over how many widths? 1, 2, 3 widths. And why am I going to stop there? Because that's how many rectangles? That's 1, 2, 3, that's 4 rectangles, right? And I created those rectangles by going to the left side of each of them. Now there's one thing in this entire formula that's not right that we need to change, because what I just did is I'm writing this for a general concept, right? For any number of rectangles. Does everybody agree with that? So what number is kind of a little messed up here? Well, this 3, right? Do you guys agree that this 3 was created by having 4 rectangles, right? So how could I rewrite this 3, this 2, and this 1, and this 0? N minus 1. Isn't this the number of rectangles minus 1? And isn't this the number of rectangles minus 2? And isn't this the number of rectangles minus 3? And isn't this the number of rectangles minus 4? Fair to say? Okay. So it's going to be n minus what to go here? So you said n minus 1. Well, so here's what I think about it, right? To get this term, right, I'm really doing it as one of these now, aren't I? So I'm starting at an n value of, well, how many rectangles do I have to have at least? 17? Good, yeah. How many rectangles do I have to have at least? I have to have at least one rectangle, right? So I have to start at 1, right? And how many rectangles am I going to actually have if I want to do this perfectly, absolutely best ever? An infinite number of them, right? So yeah, what really is before each of these guys, right? It's n minus, we'll set it, it's n minus 1, right? So what I can do is I can actually write this generally now as I want the summation of b minus a over n, that's going to be our width, right, times our length, which is f of a plus n minus 1 times b minus a over n. And so some mathematician years and years and years ago came up with that. And that represents an infinite number of rectangles on the left-hand side to get us our solution. Now, we don't need to do that, right? Because we have better ways to do it now. Guys, is this going to change if I do right side approximations? So instead of my points being there, where are my points going to be now? I'm going to start on the right-hand side. 1, 2, 3, 4, right? I'm going to go across, 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 and across. And so where would I start now? I would start at f of b, and I would work backwards by subtracting 1, by subtracting 2, by subtracting 3. Making sense? Okay? And this is what mathematicians did, and they felt very, very good about themselves. And they were proud. We know their names now. So, this right here is an example of the APCalc question, right? Something you can see on an exam. So what I want to do is I want to analyze this problem, guys, with a left side, right side, midpoint, and trapezoidal approximation. Cool? Now, this says give me an L4. So that means I want to have how many intervals? I want to have 4 rectangles, right? Boom, boom, boom. And here I want left side. So I'm going to start here, 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 and here. So what do I need to do here? Well, to get my L4, I know that I need to figure out, first of all, the width of each of the rectangles. Now, guys, do I need to come up with a formula to do this? No, because I have a limited number of rectangles. It's an approximation. By the way, get rid of the equal sign. L4 is what? It's an approximation now, isn't it? So let's go through the problem. Let's make sure we understand what we're being asked to do. Guys, this is a part of my x squared curve, right? I want to know how much area is under the curve between 0 and 1. So this little highlighted region, okay? What's the width of each of these rectangles? Not a trick question. 1/4, right? So we all agree that the width is going to be 1/4. And what am I going to do with that 1/4? Well, I'm going to multiply it by the height of each rectangle, correct? Well, where does the first rectangle begin? At 0. Why 0? Because it's a left side approximation starting at 0, right? So I'm going to start at f of 0. And then I'm going to add, okay, where's my next rectangle begin? At 1/4, right? So do you guys agree I'm going to add f of 1/4? And then where's my next rectangle begin? At 1/2. So I'm going to add f of 1/2. And then where's my last rectangle begin? 3/4. So I'm going to add f of 3/4. Just so happens that we know what the function is. It's x squared, right? So what is 0 squared? What is 1/4 squared? What is 1/2 squared? What is 3/4 squared? All right, put these together. 9, 13, 9, and 4 is 13, 14 sixteenths. I think that's right. Yeah. Yep. So I have 1/4 times 14 sixteenths. 14/64. That's my first approximation. If I do what? If I evaluate it on the left-hand side. Hey guys, quick question. I know it doesn't ask this, but why don't we see if we can answer it? Do you think this is an under approximation or an over approximation? Well, let's check. How do we do that? I go here, I go here, I go here, I go here. That's the area that I just calculated. Under or over? Yeah, this looks like an under. Looks like an under approximation. All right, so let's see what happens when we do an R4. I'm using, oh God, Picardo, change these, please. Sorry. Not equal signs, but approximations. All right, so now I'm going to do an R4. Ba-boom, ba-boom, ba-boom. And what does that mean? That means I'm going to start at 1 and work my way to the left. 1, 2, 3, 4. And hey, check it out. Left, 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 left. What's going to happen here? It's going to be a major over approximation, right? It's going to be an over approximation. Okay, so what is it going to be? It's going to be a quarter of, I'm starting on the right-hand side, working my way left. So where do I begin? At F1, right? And then I'm going to go back a quarter, so I'm going to add F of 3/4, and then I'm going to add F of, no, because what am I doing? I'm adding the areas, right? Still adding areas, same exact thing, right? So F of 1, what's 1 squared? Hello? 1 plus 9/16 plus 1/4 plus 1/16, right? I just worked backwards on this. Add all that together, and you're going to get 16, 25, 29, 30. over 64. Okay, well, I'm at least relatively confident because this number is bigger than that number, so that's at least kind of good, right? Right, guys, can we at least at this point, and I'm certainly hoping, can we at least grasp what the ancient mathematicians did, right? And how this concept works, right? And how we can get an infinite number of these rectangles by using limits and calculus. So mathematicians who first discovered this they didn't get that, right? And so they just kept trying to find better ways. And so the next method they came up with was what? Now we're going to go to, instead of the left or the right, we're going to go to the middle of each of these rectangles. So they said, okay, well, ba-boom, ba-boom, ba-boom. And they said, well, since the area of the rectangle is this times the height, they said, well, let's start in the middle. Let's start in the middle. Let's start in the middle. Let's start in the middle, because that should be a better approximation than left or right. So how do I get to the middles? Well, guys, I'm at the middle of 0 and a quarter. So didn't they just, what's the middle of 0 and a quarter? Where'd they go? They went to an eighth, right? Isn't that the middle? So they went to an eighth, and then they went to 3/8, and then they went to 5/8, and then they went to 7/8. So an M4 is going to be a quarter of this. Now, guys, you got to understand, like, a lot of people sit here and they're like, Ricardo, why did these mathematicians do this? Like, I don't get it. Like, how'd they come up with this? Like, what made them think of this? Guys, this is like early civilization in a sense, in many aspects. They didn't have YouTube. They didn't have vehicles, right? They didn't have anything to pass the time away. If you were a scholar, this is what you did, right? Scholars didn't have anybody to really teach them. They had to go to other scholars, right? And they did things like this. And they became very, 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 very famous, right? Which is why we still talk of them today, right? The more scholarly you were, the more you published, the more you wrote, the more people criticized you, but also the more respected you probably were. Okay, so plug in an eighth, right? What am I doing to an eighth? I'm squaring it. So I'm at 1/64. I'm at 9/64, 25/64, 49/64. That's going to give you 10, 35, 84 64ths, which actually is the same as 21/64. Why is that good news? It's in between my over and under approximation, right? At 84/64 times a quarter. So 4 goes into 84 21 times. All right. And then some little scholar in the ancient times came across and said, teacher. Okay. Yeah, you're right. You're right.
Thanks for fact checking.
He fact checked me. So what did these mathematicians do? They said, well, I can do you one better. And they said, let's create trapezoids, right? Most calculus is, in fact. The calc that we study and that most scholars study is ancient calc, or old, not ancient, but anything that would have been done in the last 100 years is going to be considered cutting edge research, more or less. All right, trapezoids now, right? Trapezoids. How do I find the area of a trapezoid? I take this and then I average the bases together, right? How do you find an average? You add together and divide by 2. So for a trapezoid, it's going to be a quarter times the average. So it's going to be F0 plus F of 1/4 divided by 2. And then F of 1/4 plus 1/2 divided by 2. F of 1/2 and F of 3/4 divided by 2. And so we do that one. And I promise you, I did it yesterday. So let me check and see what the real answer is. (22/64). (22/64). All right, 22/64. Sweet. I feel really good about that because it's really close to the midpoint. So it probably is pretty good, right? Use your calculator's numeric integration capabilities. And so guess what? Everything that I've just shown you has been done on the calculator. And you guys didn't know what this button was for. Now you do. If you go to calculus, there is an option for numerical integral. I want the numerical integral that starts at 0 and ends at 1 for the function x squared in reference to the value of x. What is this going to give me? The area under the curve between 0 and 1 of this function, which is exactly what we were just trying to find. 0.33333, which is pretty darn close to 22/64, right? So yeah, we got a pretty good answer, didn't we? Right? We got a pretty good answer. But again, what would make that problem better? More rectangles, right? We only did 4 rectangles. This does an infinite number of them. This is classic AP question right here. Classic AP question. Except like a part of it. Like you wouldn't get all of these parts in one question. So here's what we have. We have a definite integral. I do. Sorry. Don't.
Me study you.
Yeah, I'll both. Yeah, that's cool. Yeah, come in. Perfect. Yeah. Love it. Everything's coming together. All right, so I want to find the area under the curve on this domain, right? So the left bound, right bound of this curve. Okay, so your thought process first should be, what does it look like, right? And it is just a square root of x, right? So just looks like one of these. So I want the area under the curve between 1 and 9. Well, here's my 1. Here's my 9. So what are we trying to find? We're trying to find this. All right. Again, one of the things that we mentioned yesterday is that it's always bounded by the x-axis, right? Your area is always bounded by the x-axis. So when I say area under the curve, I'm saying until you get to the x-axis. Of course, guys, that lends the question, well, what if it's, we'll get there, right? Because the function doesn't have to be above the x-axis, does it? Could be below, or parts of it could be below, right? So we'll get to that. We'll talk about that. All right, so what are we going to do? Well, here's what they say. They say they want us to have 3 subintervals. That kind of stinks, right? That kind of stinks. So this is 1. This is, this is 9. They want 3 subintervals. So what are they doing to us? Well, they're doing that, and the problem is that 8 doesn't divide into 3 parts very nicely, does it? Right? But we'll deal with the problem. So the width of each rectangle is 9 minus 1 divided by 3. So there's our 8/3. Everybody comfortable with that? Right? So I need left side sums. Well, L3 equals, why did I say L3? Left side with 3 parts, right? All right, L3 equals, well, it's length times width, right? So it's going to be 8/3. Oh, sorry. Yeah, you're right. I keep making that mistake. 8/3 times, okay, I want left side, right? No, I want left side, correct? So that means I'm going to start here, go here, go here. Left side of each of the intervals, right? So how do I get here? What's that? That's F. That's F1. Okay. All right, guys. Now think about the last problem. How do I get from here to here? How do I get from here to here? I had to increase by 1 width, right, of the rectangle. So isn't this next value going to be F of 1 plus 8/3? Plus, well, now I'm going to do what? Now I'm going to go F of 1 plus 8/3 plus 8/3, right? I'm going to add another to that, right? And that gives me my notation, right? There's the notation of what we're trying to accomplish. Now we got to actually do it, right? All right, so that's going to be 8/3 times, all right, well, what's the square root of 1? 1 plus, what's 1 plus 8/3? Well, isn't this 3/3? So 3/3 plus 8/3 is 11/3. What am I doing with 11/3? I'm plugging it into this, right? So isn't this really just the square root of 11/3? Is that okay? All right, and then what do I do here? I add 8/3 to the next one, right? So what is this going to be? Square root of 19/3. All right, so were this a problem, guys, what would you need to have? What's the matter? What do you got? Because this is the function that I'm using, right? So I'm taking the 1 to get the height, I got to plug it into this, right? To get this height, I got to plug it into this, right? So I'm taking these, I want to make sure it's clear, guys, right? So I'm starting at 1. This is 11/3. This is 19/3. Because what did I do? Added 8/3, added 8/3. And what's 19/3 plus 8/3? 27/3, which is 9, right? And then again, so these are the x values, the y values are f of these, right? Okay, it's notation, right? It's just x's and y's. That's all we're doing, right? Now, again, on a problem like this, you'd need a calculator, right? You wouldn't be able to get, you could give me this, right? But you would need a calculator to actually evaluate this. So if that were an AP question, it would probably be in the calculator section. Yeah. All right. So 8/3 times 1 plus the square root 11/3. Oops. square root 11/3. Is that right? 12.8792. Oh, what did I do? Oh, all right. I did, didn't I? Thank you. 14.48. We'll go to the nearest hundredth. 14.48. Hey, quick question. Underestimate or over? Yeah, why do you say under? Because if I go across, go across, go across, right, the area we're calculating is below, so we're losing out on this piece and this piece and that piece, right? For a function that is increasing, it would be true. Yeah, it would be. Yeah. Yep. Of course, a lot of functions are going to waver up and down, right? You know what I mean? So now what? Well, now we're going to compare it to our, Picardo, get rid of this, get rid of this, get rid of this, get rid of this. Okay, let's compare it to the right side. So if I compare it to the right side, now I want to start here, go here, go here, correct? All right, so my R3 is 8/3 of, going to start on the right side, so starting at F9, adding F of 19/3, adding F of 11/3, which is ba-boom. Guys, isn't that just going to be 2 more than this? Oh, no, it's not. It's going to be 2, it's going to be 16/3 more than this, right? Guys, see how I did that? Because these numbers are the same as these, right? This number's 2 more than that number, right? So 2 more of these, 16/3 bigger, right? It's nice being a math teacher. (16/3) is what? Like a little more than 5. So this number should be like 19 and some change. There you go. 19.81, 19.82. Right? Then mathematicians decided, well, the midpoints are kind of dumb because the trapezoids do a much better job. So they got rid of the midpoints altogether. Right? Like, no, let's just do trapezoids. So T3, that's the average now, right? That's the average of each of the subintervals, right? So this is going to be approximately right? And to just to make sure it's clear, guys, what did I do? To make it trapezoidal, you just take the average of the left side and the right side of each what? Of each of the rectangles, right? So I'm just taking F1 and F of 11/3 and dividing it in half, right? Adding them together, divided by averaging, right? That's all a trapezoid is, right? Average. Average of the bases. All right, so put this in the calculator. Oh, what a hassle. wonder if I could do this like this. Oh, maybe I can. All right, so 3 plus this. Ugh. There we go. That works for the first one, right? Eighth, you're gonna make it?
No.
What is wrong with you? Are you mocking me out?
No.
Are you sure? As long as you're not mocking me out.
No. It doesn't matter.
I want what she's having.
Please go, Michael, please.
Oh gosh.
Oh.
Hang on, I can undo that. No, we can't have that. This should be a 1, by the way, right? Well, you will. All right, let me make sure let's make sure I got it right. Let's make sure I got it right. 8/3 times the average of the first two intervals, average of the second, average of the third. I think that's right. I better get a number what? All right. 17.15. All right. So, obviously this is the best answer, right? Now, if I asked you not to what? Not to approximate, but to exactly give me, then we are doing the minimal amount of calc that this would take, right? So this is x to the 1/2, right? So if I increase that power by 1, it becomes 3/2. What has to go in front then? 2/3. And we're evaluating that on the integral from 9 to 1. So again, what does that mean? It means take 9 and plug it in, take 1 and plug it in, and take the difference between the two, right? So that's going to be 2/3 times, well, what is this going to be? The square root of 9 cubed. Minus that. Correct? So again, this would have to be a section. I mean, you can't evaluate this by hand, okay? You can evaluate this one by hand, right? But not 9, not the square. Well, maybe you can. Hang on, square root of 9 cubed. No, you can't. All right, so if we put in the calculator, we have 2/3 times the square root of 9 cubed minus 2/3 times the square root of 1 cubed. 52/3. Oh, check it out. They gave me an answer as a fraction, which means the answer is rational. $17.33333. What do you think that's actually giving you? Giving you a repeating decimal, right? So guess that 17.3 repeating. Notice, guys, and it's, I know it's a minute detail, guys, but it's nerdy math, guy. What is going all the way across this in terms of signs? Equals, 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 because this is what? Exact, right? And these were all approximate. I don't know about you, right? But there are two things that are true right now. Thing number one, if you're sitting there looking at this and thinking to yourself, geez, you know, this isn't that bad. This is pretty easy. Like I kind of get that. I think you're going to find, guys, this course is going to get easier as the year goes on now. Okay, we've peaked in terms of level of difficulty. Okay, I think you're going to find that a lot of this undoing stuff is stuff that we've already seen because we're just doing it the other way, right? We're just doing it the other way. So a lot of review as we get ourselves towards the AP. Guys, there are sometimes going to be problems like this where, yeah, could I solve this with an integral? Yeah. Would it be? It would actually be a pretty easy one, wouldn't it? It would be, what's the antiderivative of 2x? Yeah, so it would be x squared, and we're going to evaluate it from 4 to 0. So what is that? It's 4 squared minus 0 squared, right? Which is 16. So that's an easy one to do. I get it. But sometimes we can think about these things like this. Isn't that the function 2x? If that's the point 0, 0, and that's the point 4, 8. Would we all agree that that would have to be the equation y equals 2x? So what am I asking you for? I'm asking you for the area under the curve, which is what? A triangle with a height of 8 and a width of 4. How do you find the area of a triangle? Right? So I think that connection's kind of neat. Okay. Again, what should be kind of cool to you guys now is how all of these things are starting to come together. Right? All these little topics, all these things that we've done are starting to come together.